Okay. All right, well, sorry. Let me erase this. Let me put one more dot here. Okay. So the 3 dashed lines in decreasing length. Okay, that indicates ground or the reference point. So that's our reference point. That's our reference node. So once I have this, then I'll remember that was my reference. From now on when I write equations, all my voltages are measured with respect to this point. Okay, so I'll change my color again to make sure that we keep that blue for now for our ground. So let's see. Okay, actually I meant it to be like that. So step number 2, we go ahead and assign a voltage to every other node with respect to ground. So how many other nodes do we have? One node here, one node here. So no problem, we're going to call this V1 and V2. And what we really mean is that if you take a voltmeter and you measure the voltage difference between these two, you will measure V1 volts. If you measure the voltage difference between these two, you will measure V2 volts. That's what it really means, right? Okay, so we assign voltages. Step number 3, we write KCLs for all of these nodes except for ground, right? So the overall circuit has 3 nodes, 1, 2, 3. We assign 1 to be ground, so we have only 2 nodes left. We're going to write 2 KCLs. Okay, so let's write a KCL here. All right, this guy has I1 as injecting I1 into this node. So we'll write I1. How much is the current through R1? Ohm's law. The voltage across R1 is V1, right? Here is V1, here is 0. When we have a reference node, we call it 0. So from here to here, we have V1. This current is V1 over R1. So I will write that as V1 over R1. This is all, again, with the objective of writing a KCL at this node. Okay, so that current is good. We know it's I1. This current is good. It's V1 over R1. How about this current? The current through R1. Either direction is fine, so let's pick this direction. How much is this current? Well, we're going to go back here. So we said that if the voltage on the left is V1, the voltage on the right is V2, then the current is equal to V1 minus V2 over R1 in this direction. So it's the same thing, V1, V2. The key is V1 and V2 are measured with respect to the same reference point. So the current through R2, I don't have room here, so I'm going to write it here, is equal to V1 minus V2 over R2. Okay, so I have all of the currents that are coming to this node, so I can write a KCL. I usually like it to write it as the current entering, or the currents entering must add up and be equal to the currents exiting, right? It's more intuitive that way, right? So this I1 is flowing into the node, so I'm going to write I1 is equal to the sum of the currents that are exiting the node. This current is coming out, V1 over R1. So we have V1 over R1. And this current is also going out of this node, so plus V1 minus V2 over R2. So that is our first KCL corresponding to this node. Okay, so now we need to write one more KCL, and that would be at this node. So we have to repeat everything that we did here. We have to say, what are the currents? Well, this is I2, no problem there. I2 is a current source. It wants to push I2 regardless of the rest of the world. How about R3? Well, because we have V2 from here to here, remember this is ground, right? V2 is measured from here to here. So the current through R3, according to Ohm's law, is V2 over R3. So that's good. And how about this current? You already have that, right? It's V1 minus V2 over R2. Okay, so let's write a KCL. So again, I would like to add up the currents that are flowing into the node and equate the result to the sum of the currents that are coming out of the node. So which currents are going into the node? You just look at the water pipes that are flowing into the node, right? Well, this guy is going into the node, so that's V1 minus V2 over R2. This current is flowing into the node. I2 is going this way, right? It's flowing into the node. So that's plus I2. And these two have to add up to the current that's flowing out of the node, because this arrow is going out of the node. So that would be equal to V2 over R3. That's it. So now you see that we have two equations and two unknowns. I1 is known, I2 is known, resistors are known. The only things that are not known are V1 and V2. So I have two equations, two unknowns. We solve those equations and we find V1 and V2. Okay, that's an example of how we apply the nodal analysis to solving a circuit like this. It's pretty systematic. You just have to remember these things and you just have to remember KCL, right? That's all really. Okay. Now, if you're thinking that in this analysis we did not use KVL, you are actually wrong. Remember, this equation came from KVL. So when we write this equation for the current, actually implicitly we are writing a KVL, okay? Because remember, you always need KCL and KVL to solve a circuit. Both have to be applied. So we are actually using both. Okay, let's see if we have another example. So I wanted to show you one more example of nodal analysis. So this time we pick a circuit like this. Here is a resistor, another resistor, another resistor, and then we have a current source. Then we have another resistor. Then we have another current source. Then we have another current source here. I hope my arrows are legible. So this is pointing upward, this is going from left to right, and that's pointing downward. Okay. And I just labeled these R1, R2, R3, R4, I1, I2, and I3. Let me try to make this pen a little thinner. I think it's acting up a little bit. So we'll change that to a fine point. Well, it's not cooperating. Okay, so how do we go about doing this? Okay, so as usual, we say step number one is to find the ground reference point. Again, we have all these branches connecting here, so why don't we just call this the ground? So that's the ground. Now, it seems that we always pick sort of the node on the bottom of the circuit to be ground. That's not necessarily true, but in any case, it just happens this way. Okay, then we assign a voltage to every other node. So we have V1 here, V2 here, and V3 here. Okay, so it looks like my pen is acting up on the screen. I hope you can read V1, V2, V3. All right. So in the next step, we're going to write KCLs. So to write the KCL at the node, we have to know all of the currents that are flowing to that node. By knowing, I mean we just have expressions for them. Okay, so this current is I1, no problem there. This current is I2, no problem there. We just need the current through R1. How much is the current through R1? How much is the current through R1? This voltage minus this voltage over R1. This voltage minus this voltage over R1. That's the current going through R1 this way. Okay, so KCL at that node would be V1 minus V2 over R1. Sorry, my pen is not working well. That's this current plus that current, which is I2. That is equal to I1. Okay, no, it's not good. So let me erase these and go back to a thicker pen. Maybe the thicker pen will be better. These are, you can thank Microsoft for these types of bugs that they have in their programs, but we'll survive. So let's see. Let's see, okay, no. All right, I probably have to, let's see if I can, okay. All right, well, let me just explain how this works. So at this node, we have V1 minus V2 over R1, that is this current, plus I2, these are the two currents that are flowing out of this node. We equate the sum of the two to this current, which is flowing into the node. So I1 is equal to I2 plus V1 minus V2 over R1. That is the KCL at this node. Then we go to the next node. So again, we need to know all the currents flowing to the node. So what do we know? Well, the current through R1 we know. That's V1 minus V2 over R1 going this way. This guy we know, I2 going this way. What's the current through R2? It's going downward if we divide V2 by R2. So that's going this way. And how about this one, V2, the current through R3? Well, like before, this voltage minus this voltage over resistance. So this voltage minus this voltage over resistance. So that's that current. So our KCL at this node will be I2 flowing into the node plus V1 minus V2 over R1 flowing into the node is equal to currents going out of the node. This one, V2 over R2, that's going out of the node, plus this current, which is V2 minus V3 over R3. So that will be the KCL at the second node. The KCL at the third node is similarly obtained. Here, we know the current through R3, V2 minus V3 over R3, that's going into the node. I3 is going out of the node. And finally, the current through R4 is V3 over R4. And that's known, V3 over R4. That's the current through R4. So we will write V2 minus V3 going into the node is equal to I3 going out of the node plus V3 over R4 going out of the node. And that's the KCL at the third node. So now we have three equations, three unknowns, V1, V2, V3. We can solve and we can find the three voltages. So that is another example of applying the nodal equation, the nodal approach, nodal method to the analysis of the circuit. Okay, so I hope these examples have shown you how we apply nodal equations and how we solve them. The result might be tedious, right? You have two equations, two unknowns, or three equations, three unknowns. So it might be tedious, but that's the nature of the beast, and that's how we solve circuits. Okay, this concludes our lecture today. I will see you next time.